Good morning, Professor Srijit and participants. The second session of the last day of FDP is on spectral methods in computational fluid dynamics. We have with us Professor Srijit M. From Department of Mechanical Engineering, LBS College of Engineering, Kasaragod. He had done his BTech from NSS College of Engineering, Palakkad, and MTech from College of Engineering, Thiruvananthapuram in thermal science. And he joined LBS College of Engineering in 2008. Currently, he is pursuing his PhD from College of Engineering, Thiruvananthapuram. His area of research is computational fluid dynamics. And so welcome you, sir. Please take over the session. Thank you.
So good morning, Suraj sir, Abokar sir, and all the participants. So first of all, I thank the coordinators for giving me a chance to present this session in this FDP. So today I'm presenting something about spectral methods in computational fluid dynamics. It ignores basically an introduction to fluid dynamics problem and the basic principles of spectral method and some illustrative examples what we have done in our lab during our project work is presenting. So as introduction, start with the turbulence. So turbulence is a chaotic flow of fluid particles. Now it is some characteristics are there for turbulent flow. You can say it is irregular. So there are a wide range of scales, different types of size radius are there in the turbulent flows. It is that it is three-dimensional and it is highly diffusive and dissipative. Okay, now you can see a picture here. It is a drawing of Leonardo da Vinci. So there you can see a lot of vortices there and different sizes. Okay. Now this is the basic picture given in all the textbooks which are dealing with turbulence. So it clearly defines the depicts the turbulence. Okay. So nearly all the fluid flow in nature are turbulent. That means turbulence is omnipresent. So when you go for simulating turbulent flow, fluid dynamics flows, we have to simulate turbulence actually. So all the fluid flow problems can mathematically model using an equation, so called as Navier-Stokes equation. So even though the turbulence problem or fluid flow problem is unpredictable, we can mathematically model these flows using this this equation, Navier-Stokes equation. Okay. Now this equation consists of four different terms. The first one is the temporal term, that is dou u by dou t, and the second one is the convective term u dot del into u, and then the pressure term 1 minus 1 by rho into del p, and the last term that is diffusion term nu into del square u, where nu is the kinematic viscosity. If there is an external forcing, then you have to add some forcing term also. Okay. Along with you have a delta to u equal to 0, that is continuity criteria. Then here u means it is a vector quantity. You have components in three different directions, u, v, w, and is the velocity vector, P is pressure, and U is kinematic viscosity. So the nonlinear term U dot del U can expand in terms of vorticity, and in that you have two terms. So one is convection of vorticity, and the other is the stretching term. So which is mainly responsible for the production of vorticity, and which causes the turbulence in the flow. So that is this nonlinearity, this nonlinear convective term is the main responsible factor for the turbulence in fluid. Okay. Now this energy is diffused using by diffusion terms, that is nu into del square U, that is viscous diffusion is represented by that term. And we can characterize the flow using Reynolds number, which is the ratio of inertial force and viscous force. Now, based on this Reynolds number, we can characterize the flow as laminar flow or turbulent flow. Now, in turbulent flow, we have different sized eddies. Okay, we have large eddies which are of the size of the domain, like this, and smallest eddies where the diffusion is predominant. So, just like size of the molecular size eddies, so diffusion is predominant there. So the energy is extracted from the main flow by this large eddies, and it is transferred to the smallest eddies, and where it is dissipated. So we call it as the larger eddies as the injection range, and in between energy is transferred, which are called inertial ranges. And the last part, that is where diffusion occurs, it is called dissipation range. So if you want to simulate or simulate turbulence flow, we have to simulate the smallest eddies. That means you have to simulate the eddies in the dissipation range also. Now notice, so if you want to simulate the turbulent flow exactly, we have to go for direct numerical simulation. So in direct numerical simulation, we find the flow properties like velocity, etc. It is an instantaneous velocity. So it is difficult one. So we go for some modeling. So like Reynolds average, Navier-Stokes equation, or some modeling. So you simplify the equation using some modeling terms. So if you are not using any simplification or any modeling, then you will get the instantaneous velocity, instantaneous properties directly from the simulation. That type of simulation is known as direct numerical simulation. So in any fluid flow simulation, we have to discretize the domain. Now, if you are simulating a turbulent flow, we have to the smallest size of the discretized domain should be that of the micro scale, Kolmogorov micro scale. So it is equal to the smallest eddy size. So the micro scale, Kolmogorov micro scale, it is given by eta is approximately equal to L by R e raised to 3/4. And in 3D simulation, so if you want to simulate that smallest eddy, we require to have a number of computational cells, so grid size. It will be equal to L by eta whole cube, where L is the size of the domain, okay, characteristic length of the domain. So L by eta whole cube, that means R e raised to 9/4. So it's a very large number. So even if you want to simulate a small, smallest, Reynolds number, say 10,000, we have to go for a very large grid size. So it is computationally, computational cost is very large. For if you increase the grid size, you have to go for large memory, and the computational cost drastically increases. So that means computational cost increases with the RA. So DNS also, it needs parallel processing in several computers. So if you want to have an accurate solution, we have to have an accurate method for numerical simulation. So one of such method is the spectral method. So what we are doing in spectral method, the basic principle. So if you want to solve a partial differential, so all these equations are partial differential equation. So if you want to solve a partial differential equation, it is an initial boundary value problem. So it is a time dependent problem. So you have to specify the initial conditions. You have to specify the boundary conditions. So you can represent a linear differential equation as LU. So L is a differential operator. LU is a function of space and time. U is a function of space and time. And Lux of t is equal to f of x on a domain ohm. And you have to specify the boundary condition and initial condition. Maybe it's a Dirichlet condition or a Newman condition. So you have a differential operator b u of x t is equal to g of x. So we have to solve this equation. Solve these equations means you have to find an expression for the fluid property u of x t. So it's an approximation to the actual solution. So we approximate this u of x t by finite sum of non-functions or called trial functions. So this actual property u of x t is approximated as un of x t, where un is the approximate function. So we approximate this function as a sum of trial functions. So here phi k is known as the trial function, and it is ak is the coefficient. Phi k's are trial function, so it is summed over k is equal to 0 to n. So it's a series sum. So here the term ak is a function of time, whereas the trial function is a function of space only. So the temporal and spatial terms are uncoupled. So we can change the, if you use this as the trial function, you can replace the partial differential term by using ordinary differential term. So if you want to find the spatial derivative, say the pth derivative of un, dou p by un by dou xp is equal to, say it's sigma k equal to 0 to n ak of t, which is independent of space, and it is dp dxp of phi k of x. So you have to find only the derivative of the trial function in this case, because the second term is independent of space. So you'll get the sum as akp of t. That means this is the derivative also can be expressed as a sum of these trial functions, where when in that case the coefficient term changes to akp of t. So you have to find the corresponding coefficient terms of the derivative. So you can have to find this un, that is the procedure. So in order to find un, we substitute un in the actual differential equation, partial differential equation, and find the residual. So residual is un minus ft. So we have to minimize this residual. For minimizing the residual, we use the weighted residual method. So multiply with a test function psi j and integrate over the whole domain, and it will give it indicate 0. So we will find a solution for this equation. so that UN residual will be the minimum. So sizes are known as the test functions. So depending upon the trial and test functions, we have different numerical methods. So if the trial function is a local polynomial, overlapping local polynomial, if you use overlapping local polynomials as trial functions, then such methods are known as finite difference method. It is a lower order. The polynomials may be first order or second order polynomials are used. Plus, in case of finite element method, we use local smooth functions. It is not overlapping. Local smooth functions are used as the trial functions, and they are nearly orthogonal. Or only in that element it has got value. On all other parts it is 0. So it is nearly orthogonal. And in spectral methods, we use global smooth functions. The functions are global smooth functions, and they are nearly orthogonal. So we will discuss in detail this about the spectral methods. So depending upon the test functions, we can have Galerkin method or collocation method. So in Galerkin method, we use the test function as the same as the trial function, which satisfy some or all of the boundary conditions. Then you have collocation method. In collocation method, we use a delta function. That means the test functions has got value only at grid points, and at all other points it has got 0 value. So it is 0 at all other points. So if you have different grid points, say 1, 1, 0, 2, 3, etc., with x and as the collocation points. So x1, x2, etc., different grid points. So it will be it has got a value 1 at that points only. All other points it has got 0 value again. So that is collocation method. So we discussed about spectral collocation method. Next slides. So if you use trigonometrical polynomials, say Fourier series as trial function, so it is known as Fourier Spectral Method. Okay, Fourier Spectrum. So here the trial function un of xt is taken as sum of the trial. Here the trial function is e raised to ikx 2 pi by n, where k is the wave number and x is the space variable, and n is the number of collocation, means number of grid points. So u cap, it is the Fourier coefficient. So u cap kt is the Fourier transform of ux, and I is root of -1, and k means the wave number. The differential of, so when you differentiate this, if you want to find the spatial derivative, you can directly find dou xp by dou xp un. So it's equal to, it's a sum of k is equal to 0 to n-1, 2 pi ik by n whole raised to p u cap kt e raised to ikx 2 pi n. So that means if you use Fourier series as the trial function, then that means if you use e raised to ikx by 2 pi n as trial function, then if you, so this ukt is independent of the space variable. It is dependent on the wave number on the time only, and x is coming only in this function, trial function. And if you find the derivative, so it is exponential term. So if you find the derivative, you have to multiply the e raised to ikx by 2 pi n with that e raised to ik by n whole raised to for first derivative, it is you have to multiply it with 2 pi ik by n only, and if it is second derivative, you have to multiply with 2 pi ik by n whole square. So it is easy to find the derivative in the configuration base. So if you find the Fourier transform, we call it as a configuration phase, and it is easy to find the derivative in the configuration phase. So now some details about the Fourier transform. If you consider a uniformly spaced grid, 1D grid, so xj, it is j delta x, where delta x is the different gap between the points or grid size. J is equal to 0, 1 to n. Okay, so xj are the grid points. So x is f of x is the periodic function. So if you want to find the Fourier transform, the function should be periodic. So that means the boundary conditions should be periodic in case of Fourier spectral method. So only in that case we can use the Fourier spectral method. So here again, f of x is a periodic function with a period of L, which implies that x is equal to 0 and x equal to L is equivalent n delta x are equivalent points. So if you have a one-dimensional domain, say something like this, so we start from here 0, 1, 2, 3, etc. up to the last point is n. So totally you have n plus 1 points. So in this, if it is periodic, means this first point and last point are equal. Okay. So we need to solve only the n points. The first point and last points are same. So if we take the Fourier series f of xj, it is a discrete Fourier transform. It is not continuous. So we are using discrete Fourier transform. So fj is equal to integral n equal to 1 to n fn e raised to ikn xj. So fn is the Fourier coefficient. Okay. So kn, it is the wave number. So if you take the length of this domain as L, the Fourier series, it is 2 pi periodic. So so we define the wave number as 2 pi by L into n. Okay. Now if the domain size is 2 pi, then it will be n, kn will be is equal to n. That means the wave number will be 0, 1, 2, etc. Up to n. Okay. In some cases, we have to take minus n by 2 plus n by 2 to plus n by 2 minus 1. So that depends. Okay. Then, so that's the wave number. Wave number is, if you want to find and take it as integer value, the length of the domain should be taken as 2 pi. If it is not 2 pi, you have to divide it by L, and it will be 2 pi by L into n. L is equal to n delta x actually. And f of xj is equal to fj equal to fn e raised to I 2 pi n j by n. If you substitute kn is equal to 2 pi n by n delta x, then it will be the case. Now, this is known as the inverse Fourier transform. Okay, so this is the inverse Fourier transform. And if you want to find fn, it is equal to 1 by n into sigma n equal to 1 to n fn e raised to minus I 2 pi n j by n, where n is equal to 0 to 1 to n. And this is the discrete Fourier transform. Okay, now using Fourier transform, you can find this coefficient, Fourier coefficient. And inverse transform, using inverse transform, we can go back to the physical space. So actually, when you take the Fourier transform, we are transforming the variable, that physical variable, that is space variable x and time to the configuration in frequency space. It is the wave number and the time. Okay, and this so again, next slide. So we have the general theory. Now we explain how to solve these simple equations using this spectral collocation method. Now we have a linear convection equation because dou u by dou t plus c into dou u by dou x, and c is the convection velocity which is constant, so it is linear advection equation or linear convection equation. So you have to find the derivative and equal to 0. So now you have to specify the boundary condition also. So here you are using Fourier Spectrum method, so it can be used only for periodic functions. So the boundary conditions are periodic. Now the domain is periodic in size L. So we take the case of only 1D case. So here uxt is approximated as n is equal to 1 to n un t I e raised to I n kx. It is a function of k and t. Un is a function of k and t. You substitute that expression approximation into the original differential equation. So you'll get summation sigma n is equal to 1 to n dou un by dou t e raised to I n kx plus c I n un k e raised to I n kx, because the derivative dou u by dou x, so it is so c is there, then I n kx is there. So one more time is there. Here you have k is there. I n k into un, so it's there. So I n into k into e raised to n. So that is the derivative term. So it gets to 0. Now this you have n equation and summation of n different terms are there. Now all these terms are linearly independent. To getting the error, the error function is also orthogonal to basis function. So these different terms are linearly independent. So in that case, you can equate each term to 0. So dou by dou t of un e raised to n kx plus c in un k e raised to n kx is equal to 0. So here un depends only on t, so we can take it as ordinary differential equation. So you have n ordinary differential equations and n coefficients. So you can directly using some time stepping method, you can solve this equation. Okay. Now you can use different time stepping methods for solving this equation. So you can directly use explicit methods or Euler forward difference equation for time and solve this equation. So now the whole process is made simple using taking the Fourier transform. Now actually we are solving this equation, time stepping this equation in the Fourier space. Okay. Now if you take e raised to n kx, k e raised to I n kx outside, so you have the equation dou un by dou t plus c I n un. So in Fourier space, we have to solve this only. There is no e raised to I n kx, so I can solve that equation. So that's the case of linear advection equation. So in the case of nonlinear equation, so here the nonlinear advection, because the term c, it is replaced by u. It's a velocity term. It is not constant. It is varying with u. So we have if you substitute that approximation here, then you'll get a product term of series. So you have two series and its products term. So that means you have n square terms are coming there. So it is difficult to calculate that term in Fourier space or in configuration space. So we transfer back. We first find the derivative dou u by dou x. So say v is equal to sigma n is equal to 1 to n I n k u raised to n k I k e raised to I n k. So that will give the derivative. Then we transform back to the real space or physical space, and you find the product uv, and then it is transformed back to the configuration space. So the product, the non-linear term, is calculated in the physical space itself. So then you can use that product term in the equation, and dun by dt plus un is equal to 0. So that is the ordinary differential. So you have converted that into an ordinary differential equation. So so that's a 1D nonlinear advection equation. So one thing I have forgotten here is that when you take Fourier transform, so the function ux should be a continuous function. Okay, if it is not continuous, there will be spurious oscillations in the interpolation. So that means so if you have a hat function or a if there is a function of u something like this, then if you take the Fourier interpolation, then you have highly oscillations. There will be high oscillations at the sharp changing points. So this phenomena is known as Gibbs phenomena. And so when you use Fourier spectral method, the function u or the u should be continuous. So that's about 1D nonlinear advection equation and linear advection equation. So you can solve this ODEs using simple methods. Again. Then going to Navier-Stokes equation, which is the actual equation flow, mathematical model representing the flow. So if we want to solve this Navier-Stokes equation using spectral method, there is a term. So we solve only 2D form of the Navier-Stokes equation. So we can move on to the 2D part of this equation, that is the third velocity component is omitted. So in that case, the terms in Cartesian form, it will be like this: dou u by dou t into u dou u by dou x plus v dou u by dou y. So this is the convection term, and this is the pressure term, minus 1 by rho and dou p dou x, and nu into dou square u by dou x square plus dou square u by dou y square plus fx is where fx is the external forcing term. Also, there is dou u by dou x plus dou v by dou y equals 0. That is that continuity constraint is also is there. So there is the 2D Cartesian form. Now, if you take the curl of that equation, the curl of the Navier-Stokes equation, we can transform this equation into verticity formulation. So by taking curl, you can eliminate the pressure term from that Navier-Stokes equation. So dou omega by dou t plus u dot del omega is equal to f into nu del square omega plus omega dot del u. So that is the verticity formulation. Okay, where omega is the verticity vector given by del cross u, and the forcing term small f is equal to del cross f. So in 2 dimensions, this can be written as dou omega by dou t u dot del omega f plus nu into del square omega. The important thing is that in 2 dimensions, we have only one vorticity component. So then the vorticity becomes can be treated as a scalar, and the equation will become just like a scalar transport equation. Okay. So velocity omega in 2 dimensions is dou u by dou y minus dou u by dou x. K cap, that is the direction that is perpendicular to the both direction x and y. So the stretching term, what is coming in the 3-dimensional velocity formulation is not coming in play in 2 dimension. So we can say there is no verticity generation in 2 dimension. So verticity is total verticities remain constant, or entrophies remain constant when there is no diffusion. So in 2 dimension, for more simplification, we can use stream function formulation, so that this continuity constraint is directly satisfied. So you can replace u by u and v using stream function psi. So u dou psi by dou y, comma v dou psi by dou x can v is equal to minus dou psi by dou x can be used. So if you use that, you can get the formulation dou omega by dou t. So this is the formulation: dou omega by dou t, dou psi by dou y, dou omega by dou x minus dou omega by dou psi by dou x and dou omega by dou y. So this is the convection term, and nu into dou square omega by dou x square plus. So this diffusion term, dou square omega by dou x plus the forcing term. Now, when you apply that, you have to find a coupling between omega velocity and the stream function. So from the basic definition, it will stem from that del square psi is equal to minus omega. So so the coupling between stream function and velocity is achieved through using this Poisson equation: del square psi is equal to minus omega. So you have to solve these 3 equations to means these 2 equations. So only the velocity transport equation and the Poisson equation connecting the square psi and we can solve this using spectral method. So the domain is a square domain, square doubly periodic square domain is used. Now, when you transfer a real valued function into configuration or spectral space, so the values will be complex conjugate. So you have to solve only the half of that part in the configuration part, so we can reduce the number of calculations. Okay. So doubly periodic. So we use pseudo spectral methods. So collocation methods are sometimes known as pseudo spectral methods. So pseudo spectral simulations are widely it's a widely used numerical tool for solving fluid turbulence because it is fast. So we are taking Fourier transform and the inverse transform. So only n log n calculations are coming into play when there is n modes. So the accuracy also is compared to finite difference and finite element methods. The accuracy is more, but the Toba case, it can be used only for some limited problems. Okay, it cannot be used for complex geometries. So nowadays, spectral element method, something like that can be used for more complex geometries, and also for boundary conditions also is a limitation for this type of methods. So if you are using a Fourier spectral method, the boundary conditions should be periodic. And for other boundary conditions, all Newman boundary conditions, you can use cosine transform, and Dirichlet boundary conditions, you can use sine transform, or Chebyshev polynomials also can be used. So Chebyshev spectral methods can be used for Dirichlet, where there is Dirichlet boundary conditions. Okay. So First of all, if you want to solve it spectrally, we have to transfer the variables into the Fourier space. So we have only omega, that is the velocity as the variable, and omega is approximated as e raised to I px omega p. For here, p is the wave number. Okay, k, what I have said earlier. So here, the viscous term nu del square omega, it is transferred as nu into it is summation of p over p square e raised to I px omega p. In omega p is the verticity, and the forcing term also is transferred to the configuration space. Now, in the equation dou omega by, so if you substitute that in the governing equation, so it is dou omega k by dou t. Here, omega k is the wavelength, omega k is the wavelength, wave number. Now, when you transfer the nonlinear term, so there is interaction, triad interaction between the wave numbers, which produce wave numbers which are not in the list of wave numbers what we have produced. So the new wave numbers are produced. So the nonlinear term in the equation of motion leads to difficulties in the closing motion, but it also leads to interaction among different scales. So different scales are produced. And then the diffusion term and the forcing term are coming into play. Now, for solving this equation, so you have, so actually this convection term here, what we have seen here, it is calculated using, it's a coming as convolution in the product of two series as convolution in the Fourier space. We calculate that term in the physical space, so it is marked as red. So dou omega k by dou t into f of u dot del omega minus k. So the second order derivative is converted as mu k square omega k and fk. Now, so because of wave number interactions, there is aliasing errors in the solution. So when you have nonlinear term, aliasing errors can be come into play in the solution. So to avoid that, you can use different method like two-third padding. So before transferring back into the physical space, we increase the size of the grid on wave numbers, increase the wave numbers, and then transfer to the physical space and find the product, and then coming back, transfer back to the configuration space, and which will then you can remove the extra grid points or wave numbers, so that you can avoid aliasing errors. So which is known as two-third padding. So there are other methods, spectral filtering methods are also used there. In that case, we remove the wave numbers which are more than some critical value. So that method is known as spectral filtering. So anyway, we have to avoid the aliasing errors and spectral methods. So here you have an equation. It is ordinary differential equation. You can use some stepping method for the transient term and also for the convection term. So the viscous term is again calculate explicitly. So again explicitly calculate that one, but the convection term, for convection term you have to use some time stepping methods. So viscous term you can calculate using implicit method, and for convection term you have to use some time stepping method. So you can use Adam-Bashforth method, Ringagoda method also can be used. second order, third order Adam-Washforth method are also used. Here I have represented a third order Adam-Washforth method. So diffusion term is implicitly calculated. The problem here is you have to calculate the Fourier transform. Now we have to use a faster method for calculating the Fourier transform. So we have to find the calculation. So omega k, that is the Fourier transform of velocity. So for that we have to use some method, faster method to calculate the Fourier transform. So there are available plenty of packages are available for calculating Fourier transform, fast Fourier transforms, which is known as FFT. So one of them is that FFTW3. So you can use that package FFTW3. So it is highly parallelized package. You can use it for parallel computation also. Fast Fourier transform of West. So it is available free in the net. Okay, so for the drawback of this method is that we are solving the time stepping the equation in the Fourier space. Okay, now if you want to find the intermediate results, you have to transform back into the physical phase. That means you have to take the Fourier inverse Fourier transforms. So that will increase the computational cost. But for some calculations, so when you solve these equations for some calculations, you need to calculate only in the physical phase. You cannot calculate that terms in the Fourier space. So in that case also, we have to transform back into the Fourier physical space. Okay. Now the general algorithm for the solving this Fourier spectral method is, first we initialize the value omega k in Fourier space. So that means we initialize the vorticity in the physical space and then transform it into the Fourier space. So that is possible, or else you can directly give the initial condition in the Fourier space also. Then calculate the velocity components uv based on this vorticity. Calculate u. So that means you have to calculate the stream function. So from stream function you have to calculate the uv and w. So if you know the value of omega k, you have to solve this del square psi equal to minus omega. So that is the Poisson equation for vorticity. This directly you can calculate in the spectral space, because del square will be equal to 1 by k square. So psi you can psi k is equal to, that is Fourier transform of k psi vector, stream function is equal to minus omega k by. So if you have two-dimensional solution, you have kx square plus ky square. So that will give the Fourier transform of say stream function, and you can calculate that velocity u is equal to u is equal to dou psi by dou y. Okay, then that means if you know the Fourier transform of stream function, so you can find the velocity u, Fourier transform of velocity u, that is uk is equal to kx into ky into psi k. So that directly give the velocity. So finding the derivative is easy in the configuration phase. Also, this Poisson equation. So solving the Poisson equation is very easy in the configuration space. That means psi k is equal to minus omega k by kx square plus ky square. So for each wave number you can calculate this one. So that is easy in the Fourier space. So using this equation, you can calculate the velocity components u and v. First you find the velocity and calculate the velocity components. Take the inverse of discrete Fourier transform. Inverse transform is taken to find the convective term. Okay, in nonlinear term you have to find in the physical space. So uv omega is calculated. So you can you have the terms dou psi by. So these terms you have to calculate in the this product term you have to calculate in the physical space. Okay. So uv actually you have to transfer Fourier transform of uv and omega to physical space inverse. You have to take the inverse Fourier transform. Actually, you have to find dou omega by dou x and dou omega by dou y also. So that is what we have to multiply that. That is, you have to find u dou omega by dou x and v dou omega by dou y. And calculate the multiplicative terms appeared in the initial term, that is convective term in the physical space. Take the discrete Fourier transform of the multiplicative term to get back to the Fourier space. Update the value of omega by marching on time step, and calculate the values of energy and entropy. So that's the algorithm procedure for finding the method in solution. So there are some standard velocity distributions which you can use as a benchmark. So the Taylor-Green vertex, that is, so you have a number of equally spaced vertices in the opposite vertices in the domain. So you can increase or decrease the number of vertices. So it's a time. So it has got a time in the exponential part. So you can compare the actual value. So it has got a actual solution. That means it is a function of time. Okay, it is evolving in time actually. So if you use that initial condition, after some time you can find the corresponding L square now represented by this term, and you'll get approximately a error nearly 10 raised to minus 6, less than 10 raised to minus 6 for a grid of 512 and 512. So it is so the accuracy is more for this method compared to other method. So now another solution, another example is that of a double shear layer. So that means we have a solution procedure there. So if you change the initial condition, so we have the initial condition, you have a double shear layer. So here you have one verticity distribution, and here another opposite verticity distribution. Where the equation for this initial condition is, that means at time equal to 0 we give this verticity distribution and allow it to evolve in the time. So for that I'll show the evolution in time. Okay, can you see that? So that is the time evolution of that double shear layer. So it the shear level, and because of instability, it breaks down into vortices. So these vortices evolve in time, and the same valued vortices will merge into one further. So that's a shear layer, double shear layer problem. Okay, then still with the same procedure, pseudo spectral method or Fourier spectral method, we have solved the symmetric vertex merger problem. Here you have two vortices at the center of the domain. So it's a 2-pi periodic domain, and it is separated by a distance 0. The core radius of the vortices are A0, and it has got a Gaussian vorticity distribution. That means at the center of the vortex, the vorticity is maximum. Okay. It goes to 0 at infinity. So that's the initial condition given. Now, so these two vortices will co-rotate about each other, and finally these two come closer and merge into a single vortex. So that's the show you the animation for that also. So here you can see the merging of two vertices solved using the Fourier spectral method. Now, this can be validated using the time evolution in this separation distance of these two vortices. So we can use different initial conditions, and we can solve this problem. So depending on the initial conditions, you can have different solutions. Okay. And finally, this is a two-dimensional solver actually. The application means we have some known as actually two-dimensional turbulence, which is present in soap films, etc. Now, in atmospheric air also, when the thickness of this air, atmosphere is less compared to the horizontal length. So that means when this length is very much greater than the thickness, you can approximate the flow as two-dimensional. So if your atmospheric flow can be simulated using this two-dimensional method. So also it is known as two-dimensional turbulence. It is different from the three-dimensional turbulence. As I explained earlier, in three-dimensional turbulence, we have verticity stretching term, whereas here there is no stretching term. But there is a gradient increasing in two-dimensional turbulence. The gradient is increased by the action of nonlinear term. Okay, so giving a random vorticity field in a two-dimensional domain, you can simulate the decaying two-dimensional turbulence. So initially, we will give a random vorticity, or for with a given spectrum, you can give a vorticity field in the domain and allow to evolve in time. So you can see that vortex merging is the predominant phenomenon. Vertex interactions is the predominant phenomenon in the decaying turbulence problem. So you can see the animations here for this also. So initially you have given a vorticity field something like this with a given spectrum for vorticity. So actually we are initializing it in the Fourier space or configuration space. Then its physical representation is given in here. So initially it arranges into a set of vortices, different with having different vorticity, opposite vorticities. So finally they merge, and finally at the end of this evolution, there will be only two opposite sign vorticities that exist at infinite time. So that is the decaying turbulence problem. So we can use this method to solve two-dimensional turbulence problems, two-dimensional approximated problems using vorticity velocity formulation. Okay, so the complexity of pressure term is eliminated here. Okay, so that's about spectral method. So thank you. If you have any doubts, then ask now. Suraj sir. Suraj sir.
Yes.
Over.
Okay. Participants, please type your questions in the chat box. Okay, one question is there. Can you see? Can you hear?
No.
From Dr. Amalesh Barai, what is FFTW3?
FFTW3, it's a software package freely available in the net for calculating fast Fourier transforms.
Okay. Extension to that question, can you extend whatever you have done in 2D in 3D? Or it will be very
difficult. Yeah, in 3D, but you cannot use this formulation velocity in stream function vorticity formulation.
Yeah, so that is only for 2D only.
You can use this method, but you have to formulate a method instead of stream function. There is a velocity potential function. Using velocity potential function, you can formulate that case also. But there is three different Poisson equations. You have to solve three different Poisson equations. So number of equations increases.
That's why I said it will be more difficult compared to this.
It is difficult, but more accurate compared to other methods.
Okay, yeah, right. Okay, thank you.
Okay, thank you.
Any other questions? Okay. Thank you, Professor Srijit, for
Thank
a
you. Thank you, sir.
wonderful session, and I hope this lecture would help our participants for their research and academic work. Thank you, Sri sir. Thank you very much.